Welcome, everyone. Hello. So, full stack tracing, what does it even mean? With full stack tracing, I mean, I want to trace from the top layer, which is usually, let's say, Qt JavaScript, down to C++, and then even crossing the barrier into kernel space. So that's the idea. And to give you a quick introduction, like a motivating example of why you would maybe want to do something like that, this is a story from a couple of years ago when there was a really large automotive project. They were using back then secret hardware, which became the NVIDIA Tegra X1. For those of you who know it or don't know it, it's pretty beefy embedded hardware. I mean, you could say it's not embedded anymore. The GPU is probably better than my laptop. They have 4 or even 8 cores. Everything sounded awesome, except some stuff wasn't that awesome, which we'll get to in a bit. And this being a proper automotive project, there were many, many companies involved. Each company usually had different siloed teams working on their little thing, and no one was talking to anyone except until the very last minute when they wanted to release and tried to run the software on the target hardware, and nothing worked from a performance point of view. It took far too long to boot up the HMI. It took them seconds and seconds and seconds to just show the very first frame. So what do you do in that case? The proper automotive answer is you start playing the blame game, right? You point fingers and say, you were at fault, you were at fault. And it was one of the first projects, or maybe even the first project in that company where they applied Qt. So usually what happens then is you point out the new guy, right? Qt is at fault. And that was where we were brought in, and we were tasked with help them make it faster. Show them that Qt isn't at fault. And we had a look at the code. It wasn't beautiful. It was not following best practices, but still it turns out Qt wasn't really at fault. But that was the end result that we came to. This talk is about how we even get to this stage where we can say who's to blame, essentially. My talk is helping you play the blame game, essentially, but properly, with facts, hopefully. The first thing you do in such a scenario is you fire up the Qml Profiler, right? This project actually did far too much inside Qml. They wrote pages and pages of JavaScript code. So actually we did find quite a few things inside the Qml Profiler which were plain broken, plain wrong. But something like in this picture also popped up quite frequently. What you see here is a trivial binding evaluation, taking, in this case, 180 milliseconds. This is a binding where we bind a string to the image source. And this is all we see in the Qml Profiler. The next question then becomes, why? Why does this take so long, right? You don't get the answer from the Qml Profiler. You just see that it happens, but you don't get any in-depth explanation on what happens below that Qml top layer, right? What happens beneath there? What happens on a hardware level? What happens on a kernel level? Is it maybe C++ code that's being executed that takes a long time, right? So you need to fire up more profilers and so forth to try to guess what's actually happening here. And this is what we then did, because we saw similar stuff all over the place. Sometimes you can just guess, and probably you guess right that if it's image related, then probably this is disk I/O here being slow. But we had other situations where trivial bindings took far too long, and we were shaking our heads and wondering what the hell is going on. And it turns out the explanation was answered by looking at the full stack and including the kernel layer and the syscall layer and the C++ layer. So we added trace points to Qt to the whole application, and then traced the full system, not just one application, but all applications. And we saw something similar to this. So this picture is not taken from back then. This is actually the same game example, launching same game, but with no caches whatsoever. So I just dropped my caches, then I start up same game, and you'll see this binding sometimes taking a very long time. In this case, it actually took 250 milliseconds to execute that. But here we actually see why. So the topmost, or not the topmost, but in the middle, this really wide pinkish block, that is inside the timeline, the duration of my binding being executed. I see that because there are now trace points within Qt that show me that. And then below that, I see there seem to be libraries being loaded. That's the purple color blocks. This happens because at that point, the first call triggered loading all the image format plugins. Back then, that also happened in this embedded platform. So we realized, oh, wait a minute, we probably don't need 99% of the image formats because we only have PNGs in this platform. And even worse, when you have SVG on an embedded platform, SVG, or the platform, the image plugin for that, links against Qt widgets. So you also load a Qt widget again, which again triggers potential I/O and so forth, stuff that takes a bit of time at startup. And if you want to optimize the startup time, this is something that you start worrying about and you want to remove that. And now, because I actually see what the hell is going on here beneath the QML layer, I can actually start doing something about it. So we could already optimize that by removing some of the libraries that are being loaded. Good. Because then disk I/O is hopefully going to be reduced. That's what you see on the top, actually. This is a block layer where we see which process is accessing our hard disk, SDA in this example. In the motivating example, or in the story back then, it looked actually different. There, what we saw were 99 other problems, meaning 99 other applications trying to access the disk on startup like crazy. Turns out they were emitting tons and tons of debug output, which was fed through syslog and then written to disk. And all the other applications were then hogging up the disk, which was very, very slow. I mean, the GPU is beefy, the CPU is beefy, but the really cheap flash disk they put on the board was extremely bad. And so slow that the logging overhead from other application completely killed the performance of the Qt, of the UI application. Just seeing that and increasing the I/O priority reduced the startup time from 5 seconds to 1 second, right? And it was pretty easy to show graphs then saying the I/O is at fault. It's not Qt, really, that is to blame. It's the other applications that should reduce their I/O, really. So this is the idea of this talk. How do we get from here to there? And to get there, well, back then we used something completely different, but we saw the value in that at KDAB, and we spent some R&D budget on bringing this to a proper reusable state. And we decided to build on top of LTTng for Linux. LTTng is the Linux tracing toolkit next generation. It's a pretty good tracing toolkit. It's very fast, and it's well supported on many platforms, so better use that than reinventing the wheel. But to actually get that up and running, you have to make sure that your kernel is configured appropriately. There are some flags you need to set. Especially in Yocto, this can be somewhat tricky, but it's doable. Worst case, you just drop to menu config and go to the kernel hacking traces section and activate a bunch of categories there. Then you build your kernel, you can deploy that to your device, and the next step is actually getting LTTng on the device. With Yocto, that part actually is trivial. You just enable the tools profile image feature, and then you're basically done. Make sure to install essentially LTTng tools, which is the LTTng executable. We'll see that being used in a bit. Then you have, as the second part, the LTTng modules package, which contains all of the trace points for the kernel. And then last but not least, we have LTTng UST. UST stands for user space static trace points. So this last package is what we will need for all of the Qt trace points. And maybe in the future also trace points in your own applications. Cool. Now we have the kernel configured, we have LTTng installed, and what we want next is all of the nice trace points inside Qt that we added. And this is an ongoing effort by us. I think The first stuff got merged for 5.12. It started to become really useful only recently, I guess. 5.13 is something that you should be using. But then you can just run configure-trace LTTng, and you will get UST trace points within Qt at strategic positions. So now you can take that Qt, push it to your embedded device, and start using LTTng. If you use Yocto and the Meta Qt 5 layer, we have a pull request up there. I think it got merged recently, which even allows you to just set one configuration for Yocto's Qt 5 layer, and then you get the trace points there as well. So it's pretty easy nowadays. A couple of patches you may want to apply for Qt Declarative, but I guess 5.14, you won't need the patches anymore. They will be merged by then. So we have everything set up. The next question becomes, how do we actually record something? And here I want to concentrate on this task that I used in my motivating example. I want to start tracing as soon as possible and then stop, let's say, 20 seconds after boot, and then see what happened and when did we actually see the first frame. When is the application starting to become usable? And what happened before that what led to the delay until our first frame became visible, right? What I do usually for that purpose is write a script like that. You don't have to read all of the details here, at least not now. The gist of it is that LTTng needs to create a so-called session. This is what you do by LTTng create. Then you want to enable the kernel channel, and in that kernel channel, we will enable a bunch of interesting to us trace points. I'll talk about them in more detail later on. So we'll iterate over these events and enable them in our kernel channel. And then additionally, we are going to enable all of the syscall trace points. Then finally, all of the UST trace points for the Qt tracers. And then we can actually start tracing. Eventually, we want to stop. So one way to do that, I mean, there are other ways to do that. One way is just to sleep for 20 seconds, like done in this case, and then call LTTng stop, and then you can destroy the session as well. Usually, or maybe not usually, but nowadays more and more embedded platforms are starting to use systemd as well. So we can use these two scripts that I just showed you, put them into services, and then use that to essentially run the start script as soon as possible. This is one position that is fast or early enough for my purposes. You could maybe even consider putting it earlier than that. And then after some time, in this case, after the multi-user target got started, we execute the stop script, but we will sleep for 20 seconds before actually stopping LTTng. Put together, this is what gives us the record of the first 20 seconds of my system running. And somewhere else, your Qt application is going to be run. This is an important difference to other profilers, right? We don't actually just look at our graphical application. We actually look at the whole system. Right, so now we got a bunch of data back, and if you look into the documentation about LTTng, there are even ways to stream the data over the network. You don't even have to write it to disk. And so forth. Maybe you want to use a RAM disk. I won't go into more details here, but let's assume we got a trace back. And the cool thing about LTTng is that it's able to pull this off with minimal overhead, really. I mean, you get a bunch of megabytes back, but the data in there is so valuable, it's really crazy in my opinion. That's what I love about LTTng, really. So, back then, actually, this is what I used most. I looked at text dumps of the events, but I think you all agree this is not what we want, right? In the motivating example, I showed you this nice visual graph. This is what we want to get. Back then, it didn't exist in a meaningful way. Most notably, this is hard to analyze because maybe you have, whoops, sorry. Why does it not work? It doesn't work. Okay, let me use my hands then instead. You have syscalls like the entry open add there, followed sometime later, and in between there are other events, maybe even from other CPUs, that belongs to that open add. But you get an entry and an exit, and it's hard to go from the exit to the entry in these textual forms, right? And then you have to do a lot of work in your head. There's a bubble there's bubble trace, which is on one hand the text converter that spits out this data, but it's also a C API which you can use. And this is what I then did to build a better analyzer which adds metadata on top. But if you don't have it, this is at least something already. Then you also have trace compass, which is a more graphical approach, and it's actually very, very powerful. And then also use these beautiful graphs to show and to prove that I/O was to blame. In this case, it's not too visible. Imagine disk I/O, like the red bars, go up and plateau off for a couple of seconds at start and then drop off. And then you can instantly show even management people, look, I/O is to blame, right? You cannot say anything against that. And then when you look at who is actually consuming the I/O, you see a bunch of processes that are not Qt related, and then even other silos will start to agree, yes, okay, it's not Qt that is to blame. The problem with trace compass, sadly, is that up until very recently, they did not have a good story about visualizing your custom user space trace points. So this is perfect if you just want to look at the kernel space and the system space. But for us, I want to see what is going on in QML land too, right? Maybe this is going to become better in the future, but so far it's a bit of a sad story still. Which is why we created CTF to CTF, which is a really cool name in my opinion. CTF stands for many things. In this context, it is on one hand the common trace format that is being used by LTTng. And then it's the Chrome trace format. So common trace format is very compact, very efficient binary format. And the Chromium trace format is essentially just JSON. It's incredibly inefficient. But the cool thing about it is that that you can just take that and visualize it in Chrome. And this is where the screenshot from the very beginning came from. And the cool thing is then when we do this translation from binary to JSON, we can also add more data on top, such as for OpenAdd syscall, we can translate we can memorize the file name that was used and then map that to the returned file descriptor. And if later on you do a mmap and pass the file descriptor in, you can annotate that mmap with the file name, because this is what you usually want to know, right? You want to know which file are we mapping here. So we can add a bunch of metadata on top, and we can also write very efficient trace points in Qt that do not convert UTF-16 Q strings into UTF-8 whenever the trace point is hit. We can just write out the UTF-16 data as is, and only then later on at analysis time can we convert UTF-16 to UTF-8 JSON strings and then visualize them in the browser, which makes the recording more efficient. It's an open source project. You can just check it out. Maybe a bit rough, but I've been using it happily already, and yeah, happy to get some feedback on that. Once you get one of these JSON files, then you can just fire up Chrome //tracing, open the JSON file and visualize that. And this is pretty good already in many cases, except for it being JSON and a browser context that actually does the visualization. JSON has an inherent memory limit, so if you, or not JSON, JavaScript, so if your trace file actually becomes large, it may happen that instead of this nice graph, you get this tab crashed because you're exceeding the 4 gigabyte memory limit for a single browser tab. So that's a bit unfortunate. Thankfully, that doesn't happen too often, because otherwise this UI is pretty decent already for most purposes. You see all of the processes that are going on. You see CPU frequencies, disk I/O, all kinds of things. I can only recommend trying this out. 5 minutes, okay. The problem then, I thought, could be solved by upstreaming a patch to Qt Creator to actually start visualizing the same JSON data, but in a more efficient way. And that starts to work now. We are going to push this further. But again, this is another way to visualize the same data. With that said, let's quickly then, for the last minutes, run through a couple of trace points. I think I'll skip over some of it because we're running out of time. syscall trace point, no, sorry, scheduler switch trace points are, in my opinion, one of the most important ones because these happen whenever your application gets switched out, for example, due to preemption, when another process gets the chance to run on the CPU core, or maybe it's due to I/O, and so forth and so forth. And this is a really, really important trace point you should look at. Syscalls, I believe, go without saying because they sometimes explain why the scheduler switch happened. In this case, for example, there is a read and then followed by a switch, so you can instantly see, okay, there was a serial I/O operation that triggered that. From a Qt point of view, we built TraceGen, which is a nice code generator that allows you to write really trivial files, as shown in this Qt core.tracepoints file. This then generates the quite complicated static trace points that are fed into your application, in this case in Qt, and then you can use them very, very easily inside the code. And so far, this is still private API for Qt, but in the future, we hope to make this tool available for all of you, so you can start using that in your tools as well. And the nice thing is that it's also possible to emit ETW, so event tracing for Windows trace points, with the same code, right? You don't have to write platform-dependent trace points anymore. And with that, we put trace points into Qt GUI for image reading, font database. We put a bunch of trace points into QML. Essentially, all of the things that you see in the QML profiler, you will see in these traces as well. But in addition, you get the syscalls, you get the kernel trace points, everything. And then you can add even more trace points to your C++ application to get even more information. So where do we go with that? We hope to make it really ready to use for 5.14, probably at the latest 5.15 and Qt 6. I would like to get more people interested in that, to add more trace points to Qt, to have a look at the Windows story in that regard. And with for the same game startup of about 5 seconds, I believe it's about 10 megabytes. So for a 20-second full system startup of an embedded system, it is $218 megs. And in this case, I actually started another application that hogged the disk and the CPU like crazy. So this is for 20 seconds with a trace point start script that I showed, 200 megabytes roughly. So it's very efficient. If you convert that to JSON, it's about 2 gigabytes, I believe. Any other question? If not, then thanks again. See us at our... Oh, sorry, one more question.
So the issue with measuring is it has an impact of what you measure. So what's the performance impact of all the trace points that you added there? Did you also check that?
The overhead is negligible compared to what it actually does, because LTTng goes out of its way to make it as performant as possible, which is why we picked it, right? We didn't try to build something faster because we probably would have failed. especially when you configure it properly. Like I said, there are ways to, like if your system is disk bound, you don't want to write 200 megabytes of trace file to the disk while running, right? It would completely change the results. There are ways, though, to stream the data over the network, because in the kind of context that we work on, usually the network is not the contended resource. So it's very flexible and allows you to choose whatever configuration is best for your purpose. But I can't give any exact numbers, because usually it's not there. You will see it, though, right? I mean, you will even see LTTng inside the traces and see how it affects your system, because it traces everything, including itself. Yeah. So yeah, if you have any more questions, come to our booth, see me around. Thanks for listening. Bye-bye.